Yes. Yeah. Yeah. Yes. Redo them and put those in your binder. Yeah. And I think that'll help you a lot getting ready for, the tests are cumulative. So, um, but yeah, so there should be, hey, hey, come on. So yeah, there should be two, by the end of the semester, there should be two versions of every problem in your homework. Okay. Two different times. Uh, all right. So last time, we were talking about 2D kinematics. Um, and we talked about the position vector, the velocity vector, and the acceleration vector. Um, and the relationships that we talked about are that the velocity vector is the time derivative of the position. If you have the position as a function of time, you can do it that way. And the acceleration is the time derivative of the velocity. Okay, so we've done problems like this in 1D. Let's do something in 2D where um, we have a relation, like let's say that we know that the velocity vector as a function of time is equal to, let's say, t 2t squared. And let's say when time is equal to 0, the position vector is equal to 4, 2. Um, or another way to write this equivalently, the velocity as a function of time is equal to t times the vector in the direction of the x-axis plus 2t squared times a vector in the direction of the y-axis. And at time equals 0, the position is 4i plus 2j. And we want to calculate first the acceleration vector as a function of time. And second, we want to calculate the position vector as a function of time. Um, and then let's do this too. Using the velocity and acceleration vector functions when time is equal to 2 seconds, what can we say physically about the motion at that instant? All right. Well, the acceleration is just the time derivative of the velocity. And the way you take a derivative of a vector is you just take the derivatives of the individual components. So we can think of this as if the velocity is t 2t squared, then the acceleration is the time derivative of t for the x component, and the time derivative of 2t squared for the y component. And so you get 1 4t for the acceleration vector, which you could also write as 1 in the direction of the x-axis and 4t in the direction of the y-axis. Any questions about doing that? Mechanics of it. So that's part A. Remember, as long as we're going, so this works the same way that it did in 1D. If we're going in the direction from position to velocity to acceleration, those are all time derivatives. If we're going in the opposite direction, from A to V or V to P, those are integrals with respect to time. And so if we're going in that direction, we're going to need those constants of integration. Come from the boundary conditions. Okay, so part B. So we're starting again with this velocity function that's equal to t, 2t squared. And so the acceleration as a function of time, what? Boundary conditions. So that's how we solved the constants of integration in 1D, and that's how we're going to do it here too. The thing that's different here, I mean, it's not really fundamentally different, but in 1D, we only had one integration to go from velocity to acceleration. Now we have to integrate two separate components. Each one has a different constant of integration. And so that's why we need boundary conditions for each step that you make. As you're going from position to velocity, you need that, and velocity to acceleration, you need that. Okay. If this was a 1D problem, we'd have something like at time equals 0, p is equal to 4, and that's all we need. Here we need both components. So the acceleration is the integral of t dt for the x component, and the integral of 2t squared dt for the y component. Or you can think of this as the integral of t dt. What? Oh, we're going back to, yes. So you can write this like this. The derivative of the x component, the integral of the x component, we get t squared over 2 plus, I'll call it c1. And for the y component, we get 2t cubed over 3 plus c2. Now I'm going to use those boundary conditions to find the constants of integration. So first I'll use the boundary condition for the x component. The boundary condition says when time is equal to 0, the x component of the position is 4. So at time equals 0, the x component of p is equal to 4. So we can, this here is px. This is py. Okay, so I'm going to use that x component, and we get that 4 is equal to 0 squared over 2 plus c1. And you can solve for c1. Any questions about what I did there? Yeah, so you know that this expression is the x component of position, p squared over 2 plus c1. And you know that when time is equal to 0, that expression has to give you 4. And then just do the algebra to solve for that constant of integration. And what you get in the end is that the x component of position is a function of time. Now that we know c1 is equal to 4, is equal to t squared over 2 plus 4. Okay. And now we'll do the boundary condition for the y component. At time equals 0, the boundary condition says the y component of position is equal to 2. The stuff in the blue circle is the expression for py. So that has to be equal to 2 when we set time equal to 0. So 2t, we're going to set time equal to 0. So 2 times 0 cubed over 3 plus c2 is equal to 2. And so c2 is equal to 2. Now plug that back into the expression, and we get that py as a function of time is equal to 2t cubed over 3 plus 2. So the final expression for the position vector as a function of time says p of t as a function of time is equal to t squared over 2 plus 4 for the x component, and 2t cubed over 3 plus 2 for the y component. Or you could write that as t squared over 2 plus 4 in the direction of the positive x-axis, and 2t cubed over 3 plus 2 in the direction of the y-axis. Okay. You want us to set up as the vector Kubota for that, or this one? I want you to know how to do both of those. A lot of the problems will just ask you to put it in both forms. On a test, I might ask for one or the other. Okay, so now what we have is a function of time, for acceleration, velocity, and position, we can plug in a certain time, say at time 5 seconds, and plug it into the position function. It'll tell us where the object is. So if we plug in, so where is this thing at time equals, well, where is it at time equals 0? What's its location? It's at 4, 2, which was what the boundary condition required. So that says that if you draw your coordinate system, plot a point at the coordinates 4, 2, and that's the location of the object at time equals 0. At time equals 1, where is it? 4 plus 1/2 is the x position, so 4.5. The y position is 2 2/3. So plot that point, and that's the location of the object in space at time 1 second. Okay. All right. So now we have position, velocity, and acceleration as functions of time. Now we want to figure out what's going on with the velocity and acceleration at, what did I say, time equals 2? So what can we say about the motion at time equals 2 seconds? Well, plug 2 into the velocity function. The velocity was equal to t, 2t squared. And so plug in 2, and you get that the velocity at 2 seconds is equal to 2 for the x component and 8 for the y component. If this is in SI units, then the units of this are meters per second. What direction is this vector pointing? If here's our coordinate system, then you go in the positive x direction 2, positive y direction 8, draw a vector with its tail at the origin and its head at that point, and the velocity vector looks something like that. Okay, so that's the velocity vector. The acceleration function is 1 4t. So evaluate that at time equals 2 seconds. And you get that the acceleration is equal to 1 8. And so if we plot that vector out, at this instant, at time equals 2 seconds, the thing is, to plot this point, go over 1 8. So something like this. Plot that point. It's pretty similar to the direction of the velocity, but angled a little bit more towards the vertical axis. Okay, so now what can we say about the, so let me draw these two together. So here's the velocity vector. Here's the acceleration vector. And we can break that acceleration vector up, the way we've been thinking about acceleration in the lab and in the last class. think of breaking the acceleration vector up into a part that's parallel to the velocity and a part that's perpendicular to the velocity. Okay, so the velocity is this. The acceleration is this. A little short. Yeah. I'm just breaking up the acceleration vector I just drew into an acceleration vector that's parallel to the velocity and one that's perpendicular to the velocity. Okay, so what do we know about the object's motion at this instant? Exactly. It's moving in this direction at this instant, right? That's what the velocity says. And it's speeding up because the parallel part of the acceleration is in the same direction as the velocity. And it's turning this way because the perpendicular part is to that side of the velocity.
So that means that we have many magnitudes per direction.
We have what?
We have many magnitudes per direction. So it's parallel.
Well, in this case, we know what the magnitudes are because we did it mathematically. In the labs, when we talk about it, we just think about it in terms of directions. But here, I mean, we did all this mathematically, so we know it. I mean, we didn't calculate the numbers here, but we easily could, you know. Okay, so that's sort of, that's meant to kind of illustrate first how the derivative and integral relationships work, and then how the functions for position, velocity, and acceleration relate to these parallel and, you know, to the properties of the velocity and acceleration that we've been talking about. Velocity is in the direction of the motion, and acceleration you can break up into a speeding up, slowing down part and a turning part. Any other questions about that? Yeah. Well, if we wanted the number, it would be between the yeah, we could do this all with trigonometry if we wanted to get lengths of any of those things. I mean, mathematically, a problem like this, if you get these functions, that's really all you want. But as far as understanding it intuitively, this is how you would figure out what's going on intuitively at that instant. Okay. Okay, just like in 1D, the most important type of acceleration to us is constant acceleration. We derived the constant acceleration equations in 1D by saying we're going to start with the acceleration function just equal to a constant value. And then from there, we did the integrals. And so we started out by, okay, so here's what we're going to do in 2D. And I'll try to point out similarity between this and what we did in 1D. So the acceleration as a function of time is now just going to be equal to constant ax and a constant ay. So if this is the coordinate system, you know, we're going to have some constant value ax, some constant value ay, and then this is the acceleration vector. And first, to come up with the velocity function, we're going to assume that if the velocity is equal to v0x, v0y at time equals 0, what's the velocity vector as a function of time? Okay. This is exactly what we did to figure out the velocity as a function of time in 1D. We just have more subscripts and stuff running around now because every constant vector has two unknown components. So the velocity as a function of time is equal to the integral of ax dt for the x component and the integral of ay dt for the y component. What's the integral of a sub x dt? That's right. The key thing that we're doing here, everything we're addressing here is for constant acceleration. So ax and ay are just numbers. So this is equal to axt plus c1. And the y component is ayt plus c2. We can't work with those unknown c1 and c2. So how do we figure out what those are equal to? Boundary conditions, exactly. So first I'll do the boundary condition for x, just like I did in the last example. We know that when t is equal to 0, v is equal to v sub 0. So v sub 0 x, I think is what I specified. This should be vx. So v0x is equal to ax times 0 plus c1. So c1 is equal to v0x. And so now I can put v0x in place of c1 in that velocity function. So vx as a function of time is equal to ax times t plus v0x. Any questions about that? Now I'm going to do it for the y component. When time is equal to 0, vy is equal to v0y. And so v0y is equal to ay times 0 plus c2. Solve that, and c2 is equal to v0y. Plug that back into the function we have for the y component of velocity. And you get that vy as a function of time is equal to ay times t plus v0y. Okay, you can put those two together. And you get that the velocity vector as a function of time is equal to, you could write this as the acceleration vector times t. How did we do it before? I'm going to rearrange this. Write this as v0 vector plus a times t And notice you have this equation that has the exact same form that we had in the one-dimensional case. Everything now is a vector. Okay, this V0, well, this V is made out of a Vx and a Vy. This V0 is made out of a V0x and a V0y. And this A is made out of an AX and an AY. Okay. So now we have the velocity as a function of time. Now what about the position? So when time is equal to 0, the position how did I do this before? A. So if V is equal to this at time equals 0, okay. So if V is equal to the, damn it, if the position is equal to P0x, P0y, time equals 0. Now we want to calculate the position vector as a function of time. So we're going to start with that velocity function, and we're going to integrate it. So the position as a function of time is equal to the integral of Vx dt and the integral of Vy dt. We just came up with the functions that describe the velocity. So this is equal to the integral of V0x plus ax t dt. And the y component is the integral of V0y plus ayt dt. Do that integral and you get V0x times t plus 1/2 ax t squared plus some new constant c3. That's for the x equation. And for the y component, you get V0y times t plus 1/2 ay t squared plus c4. And we're going to use the boundary conditions again to calculate those constants. So for x, the boundary condition says when time is equal to 0, p is equal to p0x. So p0x is equal to v0x times 0 plus 1/2 ax times 0 squared plus c3. So p3 is equal to p0x. And now replace that in the function. And px as a function of time is equal to p0x plus v0x times t plus 1/2 ax t squared. And notice that that function looks exactly like the one-dimensional case, except now everything that's a vector, we're using the x components instead of, because we have x and y components for each of these quantities. And now the boundary condition for y. Says that when time is equal to 0, the position is p0y. So p0y is equal to p0y times 0 plus 1/2 ay times 0 squared plus c4. And so you get that c4 is equal to p0y. Plug that back into your function for py, and py is a function of time, is equal to p0y plus v0y plus 1/2 ay t squared. Just like we did with the velocity function now, we can write this in a vector form that says the position vector as a function of time is equal to the initial position vector, that's two components of constants, plus the initial velocity times t, plus 1/2 times the acceleration t squared. So all of these formulas that we were working with in 1D, we're working with again in 2D. It's just that everything that's a vector quantity, position, velocity, and acceleration, that appears in these equations, you have to treat as two separate components for each one. Okay, so here's the take-home sheet. So here are the equations that we have. First, we have that the velocity vector as a function of time is equal to the initial velocity plus the acceleration vector times time. Second, we have that the position vector as a function of time is equal to the initial position vector plus the initial velocity vector times time plus 1/2 times the acceleration vector times time squared. And then if you fiddle with the components of these, you can come up with this new version of the third equation. So I'll break it down into A and B. The first one says 2ax times the quantity px minus p0x is equal to vx squared minus v0x squared. And the second one says 2ay times the quantity py minus p0y is equal to vy squared minus v0y squared. So when you're dealing with two-dimensional constant acceleration problems, these are the equations you have to work with. In 2D, like 1D, Um, most important application of constant acceleration is free fall. And saying free fall, I'm also including projectile motion. Right. Yep. And in free fall, the acceleration vector is 9.81 meters per second squared facing down. Okay, well, what are the components of a vector 9.81 down? But it's a trick question, so don't answer yet. Depends on what your coordinate system is. But the most common coordinate system that we're going to use, so if you choose a coordinate system with the y-axis pointing up, then the acceleration vector is equal to 0 for the x component, and down is in the negative y direction, so negative 9.81 for the y component, meters per second squared. Any questions about that? Yes, just a second. Yep.
That's only if it's like just straight up.
The y-axis, yep. That's what we're going to usually. If it's at an angle, then you need to, so what we have is this. This is our acceleration vector, okay? And if you choose a coordinate system like this, then you have to do one of those trigonometry problems to figure out what the components are. In this case, it would be in the third quadrant, so you'd have some kind of negative components for x and y. Okay. But if you choose the coordinate system with y-axis up, which is what we're going to do by far the majority of the time, and then it's just 0, negative 9.8. Question?
I was wondering, if you have, for example, if the y-axis is going down, then
Exactly. Well, let's stop there. We didn't get to any problems, but next time we will.